N-A-L-Y-S-I-S-M-S-I-S-A-N sin D of signals. Electrical and audio think signals. Engineers of psi-having stems instinctively in bandwidth terms of their think of 20 frequency KHZ of SIGA nugget query SSPO in terms NSES. Lati even ofloud their teenagers SPA frequency curs no responding spectra about up to 20 kHz. This is basically thinking in the frequency domain. In the last chapter we discussed spectral representation of periodic signals, Fourier series. In this chapter we extend this spectral representation to aperiodic signals. 3. 1. Aperiodic signal representation by Fourier integral. Applying a limiting process, we now show that an aperiodic signal can be expressed as a continuous sum integral of everlasting exponentials. To represent an aperiodic signal G(t), such as the one shown in Fig. 3.La by everlasting exponential signals, let us construct a new periodic signal Gt0 formed by repeating the signal Gt every 2 seconds as shown in Fig. 3.1b. The period 2 is made long enough to avoid overlap between the repeating pulses. The periodic signal Gt0 can be represented by an exponential Fourier series. If we let the pulses in the periodic signal repeat after an infinite interval, and therefore lim Gt0 equals Gt 2 greater than U. Thus the Fourier series representing GTO will also represent Gt in the limit to U. The exponential Fourier series for Gt0 is given by in which 62 GTO equals LDNJNCVO N equals U DN equals T10 to 22 GTO E NCVO TDT 3 1 3.2 a figure 3 1 construction of a periodic signal by periodic extension of Gt 3 1 aperiodic signal representation by Fourier Integral 63 2 and 2 and G 1/2 T 2 RR wo equals 2 RR Jo 2 A T B T 3.2b. Observe that integrating GTO T over 2 is the same as integrating GT over U. Therefore, EQ 3.2 can be expressed as dn equals to 1 OOG T EJN what T equals to 1 OOG T E 2 N NFO TDT 3.2c. It is interesting to see how the nature of the spectrum changes as to increases. To understand this fascinating behavior, let us define G, F, a continuous function of W, as G, F, equals pound G, T, EJW T dt. equals LOOG T E12 N 4 dt, in which W equals 2 RRJ. A glance at EQs 3.2c and 3.3 shows that 1. dn equals G NJO. 2. 3.3, 3.4, 3.5. This in turn shows that the Fourier coefficients dn are 1 to times the samples of G, F, uniformly spaced at intervals of JHZ, as shown in Fig. 3.2a asterisk. Therefore, 1, 2, G, F is the envelope for the coefficients dn. We now let 2 by doubling to repeatedly. Doubling to halves the fundamental frequency J, so that there are now twice as many components, samples, in the spectrum. However, by doubling to the envelope 1, 2, G, F is halved, as shown in Fig. 3.2b. If we continue this process of doubling to repeatedly, the spectrum progressively becomes denser while its magnitude becomes smaller. Asterisk. For the sake of simplicity we assume dn and therefore G, J in Fig. 3.2 to be real. The argument, however, is also valid for complex dn, or G, J. 6 for analysis and transmission of signals. Figure 3.2. Change in the Fourier spectrum. When the period 2 in Fig. 3.1 is doubled, envelope T0 G, F 0, 1 rigid, I, L, J11, near clo JL underscore G, F, less than A, B. Note, however, that the relative shape of the envelope remains the same, proportional to G, F. In EQ 3.3, in the limit as to plus U, J plus 0 and dn plus 0. This means that the spectrum is so dense that the spectral components are spaced at 0 infinitesimal interval. At the same time, the amplitude of each component is 0 infinitesimal. We have nothing of everything. Yet we have something. This sounds like Alice in Wonderland, but as we shall see, these are the classic characteristics of a very familiar phenomenon, asterisk. Substitution of EQ 3.5 in EQ 3. 1 yields 3.6. As to plus U, J equals 1, to becomes infinitesimal, J plus 0. Because of this, we shall replace J by a more appropriate notation, df, in terms of this new notation, EQ 3.2b becomes an EQ 3.6 becomes 1 d f equals 2 GTO T equals L G and D F D F E J2 N and D F T N equals U 3.7a. Equation 3.7a shows that GTO T can be expressed as a sum of everlasting exponentials of frequencies 0 plus or minus 1 I f plus or minus 2 d f plus or minus 3 d f. The Fourier series. The amount of the component of frequency n d f is g and d f d f. In the limit as to plus u, df plus 0 and gt0 t plus g t. Therefore, G T equals lim GR0 T equals lim LG ND F EU2 ND F TD F TDFON equals U. 3.7b. The sum on the right-hand side of EQ. 3.7b can be viewed as the area under the function G F D2RRFD, as shown in Fig. 3.3. Therefore, you may consider this as an irrefutable proof of the proposition that 0% ownership of everything is better than 100% ownership of nothing. Figure 3.3. The Fourier series becomes the Fourier integral in the limit as 2, 3, 1 a periodic signal representation by Fourier integral 65 G F EJ2 NFD 0 NT if F G T equals I G F J2 NFT DF 3.8. The integral on the right-hand side is called the Fourier integral. We have now succeeded in representing an aperiodic signal G T by a Fourier integral asterisk rather than a Fourier series. This integral is basically a Fourier series in the limit with fundamental frequency. Exclamation mark. F0 as seen from EQ. 3.7b. The amount of the exponential J2NN. Fort is G N LF. Exclamation mark. F, thus the function G F given by EQ. 3.3 acts as a spectral function. We call G F the direct Fourier transform of G T, and G T the inverse Fourier transform of G F. The same information is conveyed by the statement that G T and G F are a Fourier transform pair. Symbolically, this is expressed as, or, to recapitulate, and, where W equals 2 NF. G F equals F G T L and G T equals F 1 G F. G T less than equals G F. G F equals I G T EJWT DT. G T equals I G F JWT DF. 3.9 3.9b. It is helpful to keep in mind that the Fourier integral in EQ 3.9b is of the nature of a Fourier series with fundamental frequency. Exclamation mark. F approaching 0 EQ 3.7b. Therefore, most of the discussion and properties of Fourier series apply to the Fourier transform as well. We can plot the spectrum G F as a function of. Since G F is complex, we have both amplitude and angle or phase spectra, in which G F I is the amplitude and 0 grams F is the angle or phase of G F. From EQ 3.9 G F equals I G T J2 NFT DT. Asterisk, this should not be considered as a rigorous proof of EQ. 3.8. The situation is not as simple as we have made it appear. 166 Analysis and transmission of signals. F versus W. Traditionally, we often use two equivalent notations of angular frequency CV and frequency F interchangeably in representing signals in the frequency domain. There is no conceptual Difference between the use of angular frequency CV in unit of radians per second and frequency f in units of hertz Hz. Because of their direct relationship, we can simply substitute CV equals 2n f into g j to arrive at the Fourier transform relationship in the CV domain. F g t equals 1 underscore g t ej01 dt 3.10. Because of the additional 2n factor in the variable CV used by EQ 3.10, the inverse transform as a function of CV requires an extra division by 2n. Therefore, the notation of f is slightly favored in practice when one is writing Fourier transforms. For this reason, we shall, for the most part, denote the Fourier transform of signals as functions of g, j in this book. On the other hand, the notation of angular frequency CV can also offer some convenience in dealing with sinusoids. Thus, in later chapters, whenever it is convenient and non-confusing, we shall use the two equivalent notations interchangeably. Conjugate symmetry property. From EQ 3.9, it follows that if g t is a real function of t, then g j and g f are complex conjugates, that is, asterisk. Therefore, g f equals g asterisk j. Ig f I equals ig j I. 0. G f equals minus 0 grams j. 3. 1 1. 3.12 a. 3.12b. Thus, for real g t, the amplitude spectrum ig j I is an even function, and the phase spectrum 0. 8 j is an odd function off. This property, the conjugate symmetry property, is valid only for real g t. These results were derived for the Fourier spectrum of a periodic signal in Chapter 2 and should come as no surprise. The transform g j is the frequency domain specification ofthe t. Example 3. 1. Find the Fourier transform of EA1 ut. By definition, EQ 3.9a. G j equals ix ooe t ej2 nft dt equals 1000e a plus j2 rrft dt equals a plus 1 j2 n fe a plus j2 rrft lu. But 1 ej2 rrftl. Therefore 1. Therefore, as tu e less than a plus j2 rrft equals e8 j2 rrft equals 0 if a greater than 0. 1. G j equals a plus cv a greater than o. Asterisk Hermitian symmetry is the term used to describe complex functions that satisfy EQ 3. 1 1. 3.13 a figure 3.4. EA2 t and its Fourier spectra. 3. 1. Aperiodic signal representation by Fourier Integral 67, where W equals 2NF. Expressing a plus JW in the polar form as Ya2 plus W2L tan I less than L, we obtain therefore G T 0 G F equals 1 EJ tan 1 2 1 Ya2 plus 2 RRF2 IG F I equals 1 Ya2 plus 2 RRF2 T A and B 3. L3 bar. The amplitude spectrum Ig, F, I and the phase spectrum 0 grams, F, are shown in Fig. 3.4b. Observe that Ig, F, I is an even function oft and 0 grams, F, is an odd function oft, as expected. Existence of the Fourier transform. In example 3. 1. We observe that when a less than 0, the Fourier integral Fourier to t does not converge. Hence, the Fourier transform Fourier to t does not exist if a less than 0, growing exponentially. Clearly, not all signals are Fourier transformable. The existence of the Fourier transform is assured for any g t satisfying the Dirichlet conditions, the first of which is asterisk 1 underscore LG t I dt less than u. To show this, recall that J 1211 FRI equals 1. Hence, from EQ 3.9 we obtain Ig F I s.1 underscore LG t I dt 3.14. This shows that the existence of the Fourier transform is assured if condition 3.14 is satisfied. Otherwise, there is no guarantee. We have seen in example 3. I that for an exponentially growing signal which violates this condition, the Fourier transform does not exist. Although this condition is sufficient, it is not necessary for the existence of the Fourier transform of a signal. Asterisk. The remaining Dirichlet conditions are as follows. In any finite interval, g, t may have only a finite number of maxima and minima and a finite number of finite discontinuities. When these conditions are satisfied, the Fourier integral on the right-hand side of EQ 3.9b converges to g t at all points where g t is continuous and converges to the average of the right-hand and left-hand limits of g t at points where g t is discontinuous. 0.68 Analysis and transmission of signals. Figure 3.5. Analogy for Fourier transform. For example, the signal sin of t violates condition 3.14, but does have a Fourier transform. Any signal that can be generated in practice satisfies the Dirichlet conditions and therefore has a Fourier transform. Thus, the physical existence of a signal is a sufficient condition for the existence of its transform. Linearity of the Fourier transform. Superposition theorem. The Fourier transform is linear, that is, if and then for all constants a1 and a2, we have 3.15. The proof is simple and follows directly from EQ 3.9. This theorem simply states that linear combinations of signals in the time domain correspond to linear combinations of their Fourier transforms in the frequency domain. This result can be extended to any finite number of terms as I a k g k t cent equals I ac g k if k k for any constants add and signals g k t. Physical appreciation of the Fourier transform. To understand any aspect of the Fourier transform, we should remember that Fourier representation is a way of expressing a signal in terms of everlasting sinusoids or exponentials. The Fourier spectrum of a signal indicates the relative amplitudes and phases of the sinusoids that are required to synthesize that signal. A periodic signal's Fourier spectrum has finite amplitudes and exists at discrete frequencies f and its multiples. Such a spectrum is easy to visualize, but the spectrum of an aperiodic signal is not easy to visualize because it has a continuous spectrum that exists at every frequency. The continuous spectrum concept can be appreciated by considering an analogous, more tangible phenomenon. One familiar example of a continuous distribution is the loading of a beam. Consider a beam loaded with weights di d2, d3, dn units at the uniformly spaced points xi, x2, xn, as shown in Fig. 3.5a. The total load Wt on the beam is given by the sum of these loads at each of the n points. N. Consider now the case of a continuously loaded beam, as shown in Fig. 3.5b. In this case, although there appears to be a load at every point, the load at any one point is zero. This does a, b, 3. Two transforms of some useful function 69 not mean that there is no load on the beam. A meaningful measure of load in this situation is not the load at a point, but rather the loading density per unit length at that point. Let G, x, be the loading density per unit length of beam. This means that the load over a beam length LLX plus 0 at some point x is G, x, LLX. To find the total load on the beam, we divide their beam into segments of interval LLX plus 0. The load over the north such segment of length LLX is G, and LLX. The total load Wt is given by xn. Wt equals lim degree G, n LLX, d, x to 0, x1 equals 1 by 1 xn g, x dx. In the case of discrete loading, Fig. 3.5, the load exists only at the n discrete points. At other points there is no load. On the other hand, in the continuously loaded case, the load exists at every point, but at any specific point x the load is zero. The load over a small interval L, lux, however, is G, n LLX, Fig. 3.5b. Thus, even though the load at a point x is zero, the relative load at that point is G, x. An exactly analogous situation exists in the case of a signal spectrum. When G, T, is periodic, the spectrum is discrete, and G, T can be expressed as a sum of discrete exponentials with finite amplitudes. G, T equals LDNJ2 and NFOT. N. For an aperiodic signal, the spectrum becomes continuous, that is, the spectrum exists for every value off, but the amplitude of each component in the spectrum is zero. The meaningful measure here is not the amplitude of a component of some frequency, but the spectral density per unit bandwidth. From EQ 3.7b, it is clear that G, T, is synthesized by adding exponentials of the form Tj2n fort, in which the contribution by any one exponential component is zero. But the contribution by exponentials in an infinitesimal band LLF located ATF equals n LLF is G, n LLF, LLF. And the addition of all these components yields G, T, in the integral form. G, T, equals m to O lim equals L U G, n LLF, E, J n 21 RFT LLF equals 1 O O U G, J, J2 n FT DF. The contribution by components within the band df is g, j, df, in which df is the bandwidth in Hertz. Clearly g, j, is the spectral density per unit bandwidth in Hertz. This also means that even if the amplitude of any one component is zero, the relative amount of a component of frequency f is g, j. Although g, j, is a spectral density, in practice it is customarily called the spectrum of g, t, rather than the spectral density of g, t. Deferring to this convention, we shall call g, j, the Fourier spectrum or Fourier transform of g, t.